all back in this session. Yeah, let me see the chart if there is anything to be discussed. Yeah, yes.
No, we can
Yeah,
take it.
okay. So as usual, if there is anything, if you want to
Interview.
stand or discuss on the way for presentation, you can please uh, put your question or a query in the chat message. We will discuss that. So yes, we will get into the business straight away. As you can see the slide here, my slide, uh, let me go for full screen mode, right? If you can see here, it's titled as Why Study Electromagnetic Theory for Quantum Computing, right? Obviously, this is a question might have raised in most of you, right? So we need to answer this question. That's best we can do. If we do that, you would really appreciate why are we actually going through this hustle, okay, right? The quantum computing is nothing but qubits, processing qubits, and then processing qubits in a set of commands way or algorithmic way. And then we do some task and computing and do some optimization, all those things, right? There, for an outset, it doesn't appear there is electromagnetic theory, okay, right? So that's why we will get this question. Why do I need to study, or why do I need to remember this electromagnetic theory, whatever we studied from ninth standard onwards, ninth, 10th, 11th, and 12th. Okay, right? As you can see here, electromagnetic theory forms the scientific foundation of quantum computing hardware. Okay, we are seeing and getting introduced to quantum computing, okay, only from the perspective of programming. Okay, due to that, what is happening? We are thinking that electromagnetic theory may not be required as of now. That's why we are seeing this. Okay, right. And one more thing, every qubit operations or operates or interactions is described by electromagnetic theory, and it also helps us in understanding how these qubits are going out of control or out of coherence. It is called decoherence. We will check these things slightly in detail as we go through. Okay, and in fact, the qubit operations and qubit interactions and qubit decoherences are measured through this electromagnetic fields. You see, the electromagnetic fields are there everywhere. Okay, and when you are talking to the talking to the qubits means interacting through by sending some field or some light. Okay, and then this light goes and interacts and comes out. By seeing the nature of interacted light, we'll get the insights of the nature of the qubits which we have considered. Okay, so that is the main motto of this particular session. Okay, right. So let me go further and see what I have here. Okay, fine. Okay, if somebody is not able to see a small text, don't worry, I would be sharing the PPT, and here I will be discussing. So there is no hurry, no need to bother too much on the small text. So this slide I have here for you. If I talking about quantum computing, okay, an electromagnetic system and its core, because the qubits are there, they need to be interacted with. That interaction happens through electromagnetic field. You name any quantum hardware, okay, whichever way the quantum qubits are realized, in all the cases, one or the other way, the electromagnetic field is involved. Okay, so as of now, you can see the major four. One minute. Let me. Okay, just a minute. The major four ways of getting electromagnetic, sorry, qubits. Okay, here you see the major four types. All major four types I have here. Okay, where the first one is superconducting qubits. Okay, superconducting qubits are transpose. There is something called transpose, where there is a inductance, capacitance, and a resistance is there. Okay, that's a LCR circuit for you. So let me use my hand notes and talk about the superconducting qubits, and then we'll come back to our presentation. Okay, so let's take superconducting qubits. Okay, okay, let me take a little bit. Okay, superconducting qubits. Okay, this is the mostly used quantum qubits. Okay, and IBM has, okay, let's say IBM, the major player, and even Google, they all depend on this. 1 minute. They all depend on this. Okay, I need to refresh. Okay, right. So what they're consisting of is, okay, there is inductor, LCR circuit, LCR circuit. Okay, there is a inductor, not a resistor. By the way, remember it's not a resistance. Okay, inductor. Okay, and then there is a capacitor, and then some internal resistance. This is what LCR circuit is for us. Some battery is there. L, C, internal resistance, or R, any resistance, LCR circuit. What I can do, I can create a something called oscillator with this. What is being oscillating in this setup? Okay, we can realize oscillation effects. Oscillation effects. Okay, here. What is oscillation? In this, if there is anything oscillating or changing its states, is a capacitor. Okay, so the capacitor can charge to some level. Okay, let's say I'll just speak into very simpler terms. So it charges to, let's say, 100 coulomb. Okay, maximum, and after some time it may reduce or discharge, and then again it rise. Okay, and saturate. So it might drop to, let's say, 10 coulomb. Okay, and then after some time again it discharges. It's some kind of a what should I say, some kind of a oscillatory behavior. So the capacitor, the nature of capacitor is oscillating between 10 coulomb to 100 coulomb. So there is a separation of 90 coulomb charge separation is there. So quantum mechanical state change. Okay. So why this is happening? Because of the inductor, because of the internal resistance, this is happening. And I can do one more thing. I can have a different kind of oscillations by not having a DC field. This is a DC battery. Okay. What I can do? I can have an oscillatory input field. What is that? An inductor, capacitor. I don't even write another internal resistance in the other resistance, because by the way, some internal resistance would be there in a circuit. Now I'll represent the battery as oscillatory field. Okay, so some V naught, some sine omega t. Okay, with this I can have a different oscillatory effect. How different? I can have, let's say, the capacitor can exist at various charge states. One is 10 coulomb, just a minute, 10 coulomb, one is 10 coulomb, another is 20 coulomb, another is 30 coulomb, okay, and so on. So the capacitor states can exist at various levels by doing this, okay. Now, what people thought, since the separation is equal, if I want to realize a qubit between any two levels in this kind of a LCR circuit, oscillatory battery supplied circuit, it is difficult to realize one qubit across any two levels because the information it may spill to other two levels. Okay, so since that is the problem, what we will do is we will just replace the inductor, or somebody can do that. Replace inductor with this something called Josephson junction, and capacitor you keep as it is, okay, and oscillatory field, right? And even no need to have oscillatory field, you can incident some radio frequency onto the system, and whatever electromagnetic field in the radio frequency source can create some kind of a oscillatory effect on the entire LCR circuit. Okay, so Josephson junction here is JJ, which is consisting of a sandwich of superconductor and insulator. There is a superconductor, and the insulator. And the beauty of superconductor is when you cool the superconductor to very, very low temperature, let's say millikelvin, what happens? The electrons gets paired up and they form something called Cooper pairs. Okay, those are Cooper pairs. And these Cooper pairs are becoming so powerful, even they don't care about there is an insulator nearby. They even can jump through insulator into the other section. Okay, but other section also has another few more super pairs. Because of that, they may jump. They whatever is jumped will come back, and they may start doing hopping between one section to other section. Okay, and if I concentrate on set of Cooper pairs, I would be seeing certain frequencies of oscillation. Because of these frequencies of oscillation, the entire setup of LCR circuit is going to have non-linear state separation. What I mean is, because of this, if at all, if I have to have a potential well for this LCR circuit, here it is a quadratic potential well. This is a parabolic potential well. Parabolic potential for any charge, like potential particle in a box kind of a thing. Okay. Now here, what happens is the potential will no more parabolic. It's cosine. It will be oscillatory. Potential well itself is oscillatory, and within that potential, if the particle, the Cooper pair, let's say, are charged in a capacitor, it's going to have unequal separation. Unequal separation means after some time, there the orbits are going to be very closely placed. Orbits in the sense the charge states of the capacitor. So earlier it was 5, 10, 20, 15 and 20 coulomb. If you notice, you see 10, 20 and 30. This time what is the coulombic charge separation on a capacitor plate states is, let's say now first one is 5 coulomb, second one is let's say 10 coulomb, and third one is let's say 13 coulomb, fourth one is let's say 15 coulomb, and so on. If you see the separation between the orbits or the states of the capacitor are unequal. Okay, none of them are equal from each level, each two levels. By doing this, what we can have is we can have a perfect qubit realized between any two levels. Let's say this between these two levels, I realize a qubit. So these two levels are separated by 5 coulomb. There is no chance the information which I want to store between these two levels. Let's say this is a 0 cat and this is a 1 cat. Okay, between 0 ket and 1 ket, the energy separation represented in terms of capacitor charge is 5 coulomb. So this 5 coulomb separation is not there between any two levels. So my qubit is intact. My information which is stored on this qubit is intact. The same situation is not there in a previous case. So in the previous case, if you see, if I try to realize a qubit between, let's say 0 ket, 1 ket, and there are two KTs there. Between 0 ket and 1 ket, the energy separation represented in terms of charge of the capacitor is 10. And the same separation is also there between 1 and 2. If I try to realize a qubit between 0 and 1 with the information being stored with some probability amplitudes and alpha and beta, so there is a always chance that information go and spill over to 1 and 2 also, because the energy separation in terms of charge is same. Okay, so that's why the just a LCR circuit is not suitable for realizing a perfect qubit. But if I add a Josephson junction, immediately it becomes a beautiful unique qubit or unique charges, separated orbits, which would give me a qubit. Okay, you see now the way I create the qubit is inserting some kind of a radio or microwave frequency light on this. Okay, so there the electromagnetic field is there. So that's why I need to understand what is this electromagnetic fields are, what is this electromagnetic fields are generated from. So they generated from an oscillatory dipole. This generated dipole means what? The two charges are separated. Okay, right? So even for superconducting qubits, I need to know about electromagnetic fields. Okay, so let's jump back to our PPT. Fine. Now, there is another one, another zone of quantum hardware is called trapped ions. So in the trapped ions also, you see, we need to use radio frequency and laser electromagnetic fields to talk to or to even trap the ions. You might need electromagnetic fields. Okay, so you see, using the lasers, people are going to create some kind of a grooves, some kind of a locations where the ions are going to be trapped. They are not going to be anywhere. So I need to know even the solid state based quantum qubits realization using trapped ions. I should know how to do it. How to do it is answered by with the knowledge of electromagnetic fields. Okay, and there is a third one here for you. Okay, so third one is photonic qubits. Okay, so by nature photonic qubits are electromagnetic field qubits. Okay, so for the sake of other people, what is this photonic qubits are, I can tell you. Okay, so if you just take electromagnetic wave, if you take, so there is an electric field vector is oscillating. Okay, electric field vector is oscillating, and similarly the magnetic field vector would be oscillating on a horizontal plane. So electric field vector will be oscillating on a vertical plane, and magnetic field vector would be oscillating in the horizontal plane. So that is why it's called electromagnetic fields. The way it's like a light is electromagnetic field. Okay, now I can take the electromagnetic field, reduce the intensity of the electromagnetic field to such a level, I can easily, I think, able to see some bunch of photons traveling together, right? So if we are able to make a single photon eliminated from this light, well and good, that is amazing. But let's say we don't have that equipped advanced technique, advanced equipment. Let's say I'm able to extract few photons. So those photons, if I put it inside a mirrors, a perfect reflecting concave mirrors, and if I put a photon inside somehow, and that photon will be going back and forth between these mirrors. So what I'm doing, I am creating a photon confined in a small location of some reflecting mirrors. Okay. Now, if you see, photon means what? Electromagnetic field. Electromagnetic field will be oscillating. So, in this particular case, electric field is having vertical polarization. Electric field is having vertical polarization. Okay. I will say now the information of vertical polarization carries some probability because when I try to put the photon in a particular polarization, I may not succeed. I might I might succeed, but I may intentionally can also put a, polarization in terms of vertical and also horizontal polarization. So at this case, electric field vector is in vertical polarization, magnetic field vector is in the horizontal polarization. Okay, magnetic field. Now there is a way you can put the electric field polarization in the superposition state, which is vertical plus horizontal polarization. So the photon is going to have a superposed polarization between horizontal and vertical. And here I have a photon of a qubit. Okay. If you want, I can put some atoms inside. So photons would interact with the atoms. So I will have interaction between the light and the matter. So it's another field of physics. It's a quantum optics for you. So basically, quantum qubits are realized out of optical qubits or optical electromagnetic waves. So we need to understand them through electromagnetic fields. Okay. And the next one is spin qubits. The spin qubits are the electron itself, if you just take. Okay. So let me write down, this is a photonic qubits. Photonic qubits. Okay. And what did we have so far? This is superconducting qubits, and people call them as transmons. Transmons. Okay. Very important. Okay. Very good. Now, photonic qubits we just saw, trapped ions we just saw, and the spin qubits. What is spin qubits for you? Okay, spin qubits are if there is a nucleus, the electrons revolve around. Okay, so the electrons revolve around in such a way there is a rotational electric field, rotational. Uh, 1 minute. There is some disturbance here. Okay, sorry for that. Okay, the spin qubits are if you just take an electric field, electron rotating about a nucleus, it consisting of electron revolving around a particular orbit. Okay, so it is a DC current. Like electric field as electron is revolving in an orbit means a positive current would be going along in the opposite direction. So basically, it's like a current carrying loop for us. Okay, right? It's a current carrying loop for us. So with a current carrying loop, there is always some magnetic moment coming along the axis. Okay. So this is equivalent to some kind of a bar magnet for us, north and south pole. So the magnetic fields are coming like this, just like magnetic field lines for any bar magnet. Okay. So a rotational, okay, rotational motion of electron constitutes a magnetic field. Magnetic moment, if you want, you can say magnetic moment. Okay, right? So this is a rotational magnetic moment. Since it is quantum mechanical, it's a level of atomic level. So there is nothing certain. So the magnetic moment is supposed to be upward direction. Okay, magnetic moment is supposed to be upward direction, but you will not see that. Sometimes you see upwards, sometimes you see downwards. So it is called spin up and spin down. Rotational spin up and spin down. Okay, spin up, spin down. Why this is spin up and spin down is anything at a quantum level, very tiny level, things are not certain. It is a probabilistic, means they may have both the possibilities. Okay, right? Another thing is, just like our earth is rotating about the sun, it also rotates on its own axis, you see. So the electron can also rotate about itself, about its own axis. Okay, again the electron is consisting of negative charge, so it is rotating on its own axis. So what happens? Probably we might see a tiny magnetic moment due to this electron individual spin. Okay, so just a small tiny magnetic moment is there, and this magnetic moment again is not fixed in a particular direction. It could be upwards or downwards at a given point. Okay, so this is a spin down. Okay, spin down, and this is spin up, right? So spin up or spin down is even there for electron which is rotating, or nucleus also can rotate, you see. So now the charge is rotating, electric charge is rotating. Okay, so I need to know how this electric charge rotation going to induce some changes around, some fields around. Okay, so for that I need to know the electromagnetic field study. Okay, and sometime I want to change from upspin to downspin. For that, what I do, I send some electromagnetic field or light through that entity and flip it. Okay, and you can also apply magnetic fields and just do the flipping. So all sorts of things are possible just by using electromagnetic fields. Okay, right? So let's keep this aside and get back to the presentation and see one more thing. Okay, and even for neutral atoms, electromagnetic fields are going to be a very important. Why? Neutral atoms are doesn't respond to any electric field or magnetic field, but what we can create some kind of a grooves, some kind of a locations. Okay, so you see the the forest, there is something called poachers. Okay, they're smugglers. Just to catch the wild animals, you know what they do? They dig the holes and then just put some kind of a very light white sticks and cover the sticks, entire sticks, with some kind of leaves, so that animals thinks that that is a normal floor and they will go and fall. So these days is reduced. Back then, when people were smuggling elephant tusks and all, these poachers used to do make this dug, digged wells so that they can catch the elephants by forcing the elephants to fall into that kind of dug up trenches. Okay, so likewise, what we can create, we can have a sequence of, okay, right? So this is called traps. Okay, You can send a sequence of electromagnetic fields in particular direction, another sequence of electromagnetic field exactly horizontal. So you can create some kind of a locations where it is hitting with okay some potential, okay, very low potential, zero potential you mean. So zero potential means if something falls into that zero potential, it cannot come out of that zero potential, okay, because anything outside that zero potential, you will have a huge amount of potential. Okay, what I mean is, if there is a floor, if just dig a hole and leave it, if somebody falls into hole, okay, so they are at the very low level from the floor. If they're able to climb, fine. If their height is too much, they cannot climb. So we can create an electron or any neutral atom to fall into that kind of a potential well. Okay. So by doing it, what we are doing, neutral atom trap. Okay. We are using electromagnetic fields, lasers. Okay, lasers and lasers, okay, to trap. That is called optical tweezers. Tweezer means we pick something and take somewhere. So the electrons, sorry, lasers were used to create some kind of a wells where like neutral atoms are going to stuck in that wells. Okay, so you see the traps are created with electromagnetic fields. So we should know about electromagnetic fields. Okay, let me go further. So on and all, just a minute. The conclusion is understanding electromagnetic theory is therefore essential to comprehend how qubits are physically operate, whether the qubits are based on superconducting, whether the qubits are based on trapped ions, or photonic qubits, or spin qubits, or even neutral atoms. Okay, right? So I have some small figures just for some give us some idea for you people. Okay. Now, okay, coming back to something called the coherence. Okay, people always talk about, the moment they talk about quantum computing, they talk about qubits, and qubits are noisy in nature, and the entire computing is noisy intermediate scaled quantum, NISQ quantum, NISQ. So that is what people say. So what they mean is the qubits realized are not perfect. Okay, right? Uh, you take any kind of a qubits, whether it's a uh, whatever qubits we just saw so far, there always have some kind of a noise. So perfection is not possible. Even a topological qubits, there also we might need to interact and talk to them using electromagnetic fields. So there also we might need to ensure the perfection, but it's not possible. But as the technology improves, that may be possible in future. But as of now, we're in the NISQ era. Okay, so as you can see in my slide here, this errors are creeping in because there is a system is not behaving as per my requirement for a very long time. So which is measured using a quantifier called a coherence. It is called coherence. There are two types of coherence times associated with any kind of a qubit. Let me explain what is that. Okay, right? So point, we want to understand the coherence. Okay, right? So let's take a simple qubit from a theoretical point. The qubit can be any kind, but its nature is expressed as two superposition state system. Okay, right? A quantum state is represented as alpha 0 plus beta 1. Point. Now, what you see here is if I have an electron initially is in the ground state, the moment I realize a qubit means this electron is going back and forth between ground and excited, and at any given point, if I try to catch and see where it is, it will falls to one of the state. It's like tossed a coin. So tossed coin, if if you ask even a small kid, he say, what happens when I toss a coin? It will falls to one of the state, or if somebody catches it will falls to one of the state. It's a head and tail. Okay. Now this is superposition state for us. Okay. Now the thing is, this superposition state is not guaranteed forever. Okay. Right? Why it is not guaranteed? There are two reasons. One reason, first reason, if you take any atomic system, okay, if there is an electron which is raised to the excited state, okay, and it goes to the excited state, excitation, it goes to the excitation, it remains in the excited state for roughly about 1 microsecond. 1 microsecond. It can't stay more than that. On an average, I'm talking about. So about 1 microsecond it can stay. After that, it just decays. Okay, and it decays and it falls to the ground state. If there is any other states available, it may falls to other states and emits the energy corresponding to that transition. Okay, right? So the excitation lifetime is about some order 1 microsecond. Okay, so that is the number. It is called T1, 1 microsecond lifetime. You can say excitation lifetime. Now, because of some problem, okay, because of the environment around, even before 1 second, the electron just decays back to the ground state and it is no more staying in the excited state. Because of that, what happens? I intend to do the computation by keeping the electron in the excited state. I intended, but the problem because of this, I will lose the chance of using that full time for doing a computation. I am okay, I think that I'm able to do it, I'm doing it, but in fact what is happening, the system went out of my order, and what is happening, I'm losing the control, I'm losing the computing capability, and the errors would be creeping in. So the lifetime of excitation, which is T1, is going to create a problem for me in computing. It is a decoherence. Okay, coherence means something in order. So this is a T1 decoherence. Okay, so the qubit, again I'll come to that, for having 1 microsecond excitation and then come back, then go 1 microsecond excitation. So there is a sequence of excitation goes back and forth for the electron. Having that kind of a excitation and de-excitation, I need for realizing a superposition state. If I need 1 microsecond apart excitation and de-excitation, but it is less than that, in that case, the qubit realized for me is a problematic qubit. Okay, and the next decoherence factor is, now let's forget about excitation lifetime. Let's talk in terms of, let's say I have some kind of a oscillation created by some means. Now you see, any oscillations cannot sustain forever. If you just take a pendulum and oscillate, it oscillates for some time, and then what happens? It loses its amplitude and comes back to stationary equilibrium state. That is due to magnetic earth gravity. Okay. So similarly, the lifetime of oscillations would also be having some damping effect. What happens is the oscillations in time, if I just notice, the time versus oscillation for a qubit, if you notice, initially the lifetime of oscillation is something. After some time, the oscillations may die down. Okay, so there is a time span within which I have a intact oscillations. This time span is called T2. Okay, so this T2, after T2, what happens? There is a no oscillation, no superposition at all. So because of this, what happens again? I end up in not able to do the quantum processing. Okay, so this is losing the oscillations before the T2 time because of the environment around, because of some noise around. I will have again the decoherence. Okay, you see, again the decoherence is coming. So on and all, there are two ways I can see for a qubit to have a decoherence. One is T1, another is T2, and one is called horizontal and one is called vertical or longitudinal, and yeah, something like that, longitudinal and I think vertical. So the idea is T1 and T2. So here in my slides, what you see here, we have a figure coherence errors. Okay, right? So the simplest example I would usually would like to give it for anybody to understand the coherence is, if I intend to do a computing with certain number of qubits, I want all the qubits to behave in a one way, but because of some qubits which are close to the surrounding environment, some are shielded from the environment, okay, which are there at the center. They may not interact with the surroundings. What happens in that case? The ones which are very close to environment, they extract and interact with the environment and extract some energy from the environment, and they just loses the syncness with the existing other qubits. So in that way, I might lose the control and I might do some kind of a wrong calculations in my computing task. Okay. So here if you see in my slide, I have noted here the quantum decoherence sources. Okay. The fragility of quantum states stems directly from electromagnetic disturbances, right? So one is the charge noise. Fluctuating electric field destabilizes the qubit state. Okay, if there is some kind of a fluctuation in the field which is creating the superposition, so that fluctuations would create a noise. Okay, and there is something called a magnetic interference. So the stray fields introduce 1 by F and some effect, something called Johnson noise. So even having some other electromagnet or a magnet around would create a T1 T or T2 kind of a decoherence. Okay, there is something called radiation losses, uncontrolled electromagnetic EM wave leakage that is will happen. Okay, right? So sometimes even the qubits interact and they impose a deformance between each other. So that is called a crosstalk for you. Okay. So all and all, if I want to represent this noise induced decoherence graphically, it's very simple. I use the black sphere representation. You see, I intend to keep the excitation, let's say excitation is represented along the positive z axis. What happens? Because of noise, this positive z axis pointing electron or excited electron would drop to the ground state, okay, and because of the noise. Then again, I have to put it back. So I may need to use some kind of extra electromagnetic fields from around. Okay, right? So that is one thing. And one more thing is, let's say by somehow I created a superposition state. See, on an equatorial plane of a black sphere, if you remember back, okay, black sphere representation. I quickly give the black sphere representation for you. Okay, so if you have a quantum state alpha 0 plus beta 1, it's a two-dimensional vector for you to represent graphically on some way. what we can do, we can introduce alpha is equal to some cos theta by 2, beta is equal to exponential I phi sine theta by 2, where theta is a polar angle and phi is a equatorial angle of three-dimensional spherical coordinate system. So, three-dimensional spherical coordinate system is, okay, something like this. Okay. Now, this is Cartesian coordinate system, I, J, K. I use a Cartesian coordinate system to show where the spherical coordinate system is there. Okay, there is equatorial plane. I have a sphere. Okay, you take any vector, it makes an angle theta with the z axis, and if you just to drop a shadow of it onto equatorial plane, that equal shadow makes an angle phi. Okay, now you see any point on the surface of this three-dimensional entity or two-dimensional surface of the sphere will have theta and phi representing each point. So that theta and phi I use to create alpha and beta. So a cubit is represented on the surface of the sphere. Okay. Now on the north pole I'll have 0 bit. Okay. On the south pole I'll have 1 bit. Anything other than north and south pole, what we have? We are going to have remember, a superposition state, means equal combination or some combination of zeros and ones. Now along the x-axis, if you just notice, along the x direction, okay, we will have theta would be what? Theta would be pi by 2. Okay, and when theta is equal to pi by 2, alpha is equal to cos pi by 4, so which is 1 by square root of 2, and beta is also exponential I phi, okay, exponential I phi cos theta, sine pi by 4. What is sine pi by 4 for you? 1 by square root of 2 again. Okay, basically alpha beta are both are 1 by square root of 2. Now there is an exponential I phi is there. Because of the exponential I phi, I'll have some fixed theta phi value. Let's say for simplicity, let's take phi is equal to 0 at some point, which means alpha and beta both are equal to 1 by square root of 2. So this is pointed along the x-axis. Cubit is pointed along the cubit pointed along the x direction. Now this is how superposition I created. Now because of the T2 decoherence, what happens? It's the qubit supposed to point only along the x-axis. It is not going to point along the x-axis. It slightly deviate from the x-axis, slightly precess about some axis. So that is what showed here in the bottom left. Okay, right. Let's terminate. Yeah, you see in the bottom left, you see the qubit supposed to point along the x-axis. What is doing? It is slightly going away from the x-axis, acquiring some phi value. So that acquiring phi value is represented some gamma phi, which is a inverse of t2 time. It's a rate with which the decoherence is happening because of the loss in the oscillations. Probably oscillations may be there. Okay, right? So if the oscillation is completely lost, what happens? The cube is going to fall into one of the state, either 0 or 1. Means it is going to point along the z positive or z negative axis. Okay, so you see in all the cases transition is done with the supplying energy, or even losing a kind of a coherence is also described in terms of electromagnetic energy. Okay, so that's why we have to understand about electromagnetic field processing in the computing. Okay, so let's see now one more. 1 minute. Okay, what quantum? Okay, when it comes to processing, we will be using quantum gates. Okay, right? Quantum gates are realized out of electromagnetic pulses, right? So you heard about Hadamard gate, you see? Okay, so this is, let me give a name for this. Okay, what is this? The first one is coherence understanding. So this one is decoherence of T2. Okay, okay, now let's next go ahead and quantum gates. Okay, realization using, okay, quantum gate realization using EM waves or pulses, electromagnetic pulses. Okay, so why is this so? As you can see, right, in our block sphere itself, if the qubit is pointing along the x-axis, sorry, along the, 1 minute. Okay, if qubit is initially along the 0 direction, if I rotate that about y-axis, okay, about y-axis, if I rotate by 90 degrees pi by 2, what I am going to get? I am going to force 0 to become 0 plus 1, 0 plus 1. Okay, 1 minute. Reload. Just a minute. Huh? This is small glitch. Yes. Maybe I have to save this. Export as image. Yeah, just to ensure that we should not lose. 0 to 1 divided by square root of 2. Okay, so rotation about y-axis with the pi by 2 angle. If I do that, then I'll get a superposition state. So basically, what are you doing? You are rotating a quantum vector pointing from north pole to equatorial plane. Okay, so how is this vector rotation is possible? You simply do Hadamard gate operation. You see, Hadamard gate operation is 1 by square root of 2, 1, 1, 1 minus 1. You take Hadamard gate, act on 0, you are going to get 0 plus 1 divided by square root of 2. So this is on paper. But what goes in the experimental lab is the experimentalist would create a pulse of pulse area, okay, right? A pulse of pulse area which is pi by 2, okay. So that pi by 2 pulse area pulse you will take and you will introduce the energy, okay. We introduce the energy, 1 minute. Disabling. Yeah. Okay, pi by 2 pulse. The area of the pulse is pi by 2. What is consisting of? It consisting of sequence of photons, let's say, are placed 1 microsecond apart. Okay. Why there is a sequence of placing of these photons is 1 microsecond apart is why? Because I want the electron to go to the excited state and stay there for 1 microsecond. After that, by the time it is about to come down, I'll send one more photon, so it goes up. So basically, what I'm doing, I'm trying to create some kind of a juggling effect. Let's say we juggle things. Okay, we just do some kind of a juggling or oscillations. So using a pi by 2 pulse, we are creating it. Okay, so the gates are actually realized out of electromagnetic pulses. Okay, whether you take a superconducting qubits, right, an ion or neutral atom based case also, we see the Rabi oscillations, we see Raman Stokes and anti-Stokes. In all the cases, electromagnetic pulses are going to be very, very important in doing a quantum state manipulation. Okay, so when it comes to spin qubits, right? So this is they are actually responsive to the external magnetic field. They are like magnetic moments. So there, I might need some kind of a magnetic field-based resonances or pulses needs to be sent onto the spin qubits to have some kind of a oscillations, a controlled oscillations, or controlled coherent state of superposition. So in that way, I can realize a spin qubit. Okay, right? So if you notice all these three cases, what you notice is electromagnetic theory explains the fundamentals here. The field matter interaction it explains. It explains the oscillation of electron. It's called Rabi oscillations. It explains the Maxwell block equations. Means it explains how the energy of incident electron as a photon transferred to a material. Okay, and this there's a pulse shaping and pulse area and bandwidths are involved here. So those things are very much crucial in the case of designing a gate. So without knowing all these things, it's impossible to do the quantum information controlled processing. Okay, so that is a conclusion here in this particular slide. Okay, let me go a little bit ahead. 1 minute. Okay, right. Okay, so in the case of cryogenic microwave engineering and pure applied electromagnetic wave scenario is involved. Okay, so the mainly the transform based quantum computer. So what you see on the right side is a simple chandelier picture you see in IBM and all other transform based quantum computer cases. Okay, so what you see, there is a level by level there is some kind of a divisions. So these are all connected by some optical waveguides. Okay, so these are radio frequencies are going through it, and ultimately they go and talk to the quantum chip at the bottom. Okay, so at that point, what is happening is a cooling needs to be required done so that the qubit realized out of this transmon is intact, because there is a superconductive to happen for a transmon to be active. So the cooling is done at cryogenic temperatures. Okay, right? So a building scalable quantum processors demands a sophisticated microwave engineering. Okay, and a direct application of this. This is a direct application of electromagnetic theory. Okay, right? So when it comes to transmission architecture, okay, there is a microwave resonators here, there is a coplanar waveguides are here, and there is a 3D cavities are also involved in this structure. And we work for all the minimum loss and precise coupling between these things. It's very, very important. So electromagnetic theory plays a vital role there. And when it comes to signal processing, let's say I want to send some information and retrieve the information, and I have to do a properly some kind of a processing. So I would be using some filters, attenuators, and isolators for cleaning the signal from the noise. Okay, so this is another zone of information processing, signal processing in this case, which is done with the knowledge of electromagnetic field processing. Okay, and and so there is an amplification is also involved in this kind of a setups. Okay, so these are called they have to work at a very low temperature, cryogenic temperatures. Okay, so they work at a millikelvin, and we need to know even that cryogenic level how these electromagnetic fields are going to play a role in realizing the qubit processing. Okay, right. So let me go further. Okay. So how many slides? Okay, 6 slides we have. I think we need to wind this up soon and then get into the actual the electromagnetic theory. Okay, I'll take another 5 to 10 minutes and we'll give a gap. Okay, so right there is something called readout, information readout, or detecting the state of a qubit, which is actually done through electromagnetic fields. Okay, and we need to measure the qubit, so we will be using electromagnetic fields for that. Okay, we need to have expertise in electromagnetic field, so that is actually listed here. There is something called cavity QED interactions. Okay, so there will be cavities involved here in this case. Okay. Now, quantum algorithms for electromagnetic based problems. Okay. So there's a closing this. There's a entire thing is interconnected. So what is involved in this case is there is a Maxwell's equations are involved, photonic systems are involved, electrostatics is involved, magnetostatics are involved. So altogether, you see there is interconnection of all these things. They're all the parts of the electromagnetic theory. Okay. Now there is some mathematics also there. It's actually called it is called it is called a vector calculus or a mathematical physics. Just a minute. Hmm. It is called vector calculus. So we will touch those things. Okay, right? And the quantum physics is starting with the wave theory duality or wave nature duality. So even though it's a part of quantum physics, that part is also dealt little bit here in electromagnetic theory. Okay, and all our electromagnetic theory representation, let's say you start from Maxwell's equation, they all involve differentiation, differentials, or divergence, or gradient. They're all partial differential equations. So that is also involved. So irrespective of not having any mathematical background, if you have electromagnetic theory, which is easily dealt in that by default. Okay, and there is advanced methods like green functions, special functions there actually, and boundary value problems are actually involved in the electromagnetic theory. Okay, fine. So yeah, fine. Let me go further. Okay, so the scaling demands, I'm not just ending up with a single qubits. I want to have multiple qubits together, connected, interconnected, and I want to minimize there is a cross talk between them, and how to wire them, how to route them. Okay, how to do kind of a mode engineering, shielding the system from the surrounding. These are all actually very important scenarios one should have, and designing them. Okay, design into one package without having any problems. Okay, let me conclude with to one page. Yeah. Yes. So altogether, what you see in the last 1 hour, electromagnetic theory is not a peripheral; it is essential for us. Okay. So whatever I'm going to start and discuss in the next one session and tomorrow sessions, 2 sessions, it is a part of electromagnetic theory. It is not going to be a useless content. It is a very vital content. Okay. Fine. So let's see. There is questions here. A couple of questions. One is how about topological qubits? Do they depend on electromagnetic fields? Of course. How are you going to realize them, or how are you going to interact with them? how are you going to process them and change their status is through some kind of a electromagnetic fields. Yes. Okay. And the next question by one more of our colleague. Quantum computers require very low temperatures. Okay. Then how we see IBM or a Google employees holding a chip like thing in their hands, saying it's quantum computer, won't it affect the chip? Yeah, for the display, probably they may have some kind of a dummy pieces, they may show it. But when it comes to the actual, the one which is they're going to install, it's going to be very delicate. They have to carefully handle it. They may use some glosses, but what they're showing is just a transport based chip. Okay, a simple LCR circuit where the capacitor plates are actually etched or layered. Okay, and Josephson junction is also going layered or deposited onto the chip, and they are going to realize the qubits out of those interconnected LCR circuits as a single qubits interconnected. It's a network of qubits. Okay, so that entire chip is going to be cooled down. Okay, if you can check the architecture of any IBM computer, anything, so basically the chip is going to come at this point. You see, 1 minute, 1 minute. So chip is going to come at the very bottom here. What you see the chandelier picture. Okay, so this entire thing is enclosed in a large drum. Okay, layer by layer, they fill liquid helium and liquid nitrogen and liquid hydrogen and so on, so that the bottom temperature is going to be about 50 millikelvin. So when it is in working and it's processing information is going on, at that time the chip is connected to this all the waveguides and it is enclosed inside a large container. Okay, right? Fine. So there is one more question here. Vinod Kumar Chauhanji is asking, please tell electronics gate and quantum gate both are same or different? A very good question, sir. Okay. Let me use my hand notes here. Okay. See, electronic gates are what? Okay. Right. So electronic gates were realized out of what? A transistors. Okay. A transistor is there, is in on state, and I want on state means let's say its output is 1. I want to convert that into off state, a 0. So what I'll do, I just play with its gate. Okay, transistor gate to emitter. So the transistor, if you just take, okay, transistor, there is a gate or a base. Okay, 1 minute. There is emitter and the collector. Okay, so the voltage difference between gate or a base to the emitter is going to play a vital role. Whether we have a transistor is in the, okay, this is an emitter, this is a collector, this is a gate. Okay, so this voltage between these two, the bottom two, decides whether current should go forward or not. Okay, and if the current is going forward, let's say on state, if it not, it's off state. So basically, if there is a zero signal I want to convert, I send through a NOT gate operation, 0 becomes 1. So basically, from 1 to 0, I do it by NOT gate operation. Okay, and there is some other gate operations I can realize like an AND gate operation. So there are two inputs and one output. So A and B giving me some C and operation. Okay. So these are like gate operations were realized using some transistors. You see? Okay. So these are electronic gates, conventional electronic gates were your right? Basically consisting of some uh, transistor management or engineering. And when it comes to quantum gates, it is completely different. How different? Okay, so there you see in electronic gates, we are talking about billions of electrons going through some gate operation and showing some changes in their state. But when it comes to qubit processing, we have quantum gates. So the quantum gates are talking in terms of, or we are talking in terms of the state of single qubit, state of single atoms. Okay. So the atom is in the ground. I want to make it to a superposition state, like a plus state. How I am going to do? I am going to do it to act Hadamard gate. What is that Hadamard gate? It's a pi by 2 pulse. Okay. So the gate operation here is supplying some energy. Okay, a controlled manner supplying some energy is a quantum gate of Hadamard gate. Okay, sometimes if there is a plus gate state is there, which is 0 plus 1 divided by square root of 2. I want to make it a minus gate state. What do? I just do a Z gate operation. So as we know, Z acting on plus is going to give you a minus, right? So this is also another kind of a field interaction and introducing a relative phase between 0 and 1 by flipping the like a probability amplitude nature of one gate. So again here the gate operation is done through some electromagnetic field incident on the qubit. Okay, so the quantum gates are not just like electronic gates. Quantum gates are, in fact, when it comes to materials, for sure, it is based on some energy, some pulses of electromagnetic field. When it comes to, let's say, photonic based qubits, now the energy electromagnetic wave, it is itself, electromagnetic field itself is a qubit. In that case, how this qubit is going to be processed? The qubit is going to be processed using something called, let's say there is a electromagnetic wave or a photons are having a vertical polarization. I want to convert that into a horizontal polarization. What do? I'll just use some kind of a wave plate which rotates vertical to horizontal. Okay, half wave plate people call, or a quarter wave plate. So the horizontal vertical polarization becomes a horizontal polarization going through this wave plate. So basically electromagnetic wave oscillation is happening in vertical plane becomes a horizontal plane. So this is a rotation effect of horizontal to vertical to horizontal. Okay. So here these plates are made up of some materials, some transparent materials. So the gate operation is done with this transparent wave plates. Okay, right? So you see there is a catch here. If I have a qubits realized out of a material, the nature or state of a material or a qubits is changed using electromagnetic waves. So electromagnetic waves allows us to realize gates. If the qubits are realized out of electromagnetic wave, so in that case, what happens? I use a material-based gates to change state of the qubits. Okay, so the electromagnetic waves as qubits. Okay, and this is a material as gates. Okay, right? So in the case of, let's say, electrons in the state or a qubit, okay, a qubit, in this case the change from one form to another form, let's say z gate, realized using em waves or pulses. Okay, em waves or pulses. Okay, I hope I answered your question, Vinod ji. Right? So there is one more question. Do various types of qubits give different efficiencies? I mean, which qubit is more preferred? A very good question. Okay. So there are various ways of realizing a qubits. We saw few: photonic, spin qubits, neutral atoms, ion trap atoms. Okay. So what is the third one? Okay, there's a five, more or less five we touched. All those cases, if you see, the lifetime of coherence is different, and some of them give a large coherence time. The number of operations I can you do in that large coherence time is little bit less. Okay, so then there is always a balance. If you go for large coherence time, the number of like a number of operations you can, like operation time would be something. If the coherence time is low, even in that case there are qubits which give a lot of operations on that. So it doesn't mean the large current time is always better for doing computation. Nothing like that. So there is always, you have to see how much lifetime coherence lifetime a qubit gives. What is the time taken for one operations on that qubit is very, very important. So that's why there are various ways, but people choose a best combination. So looking at the current technology development, if you see, there is a large lenience or leaning towards transmon kind of a superconducting based qubits is being explored so far. Probably they are best because they are called artificial atoms. I can mimic the new real world atoms with LCR circuit. That's why people are preferring. But these days, some other solid state based qubits are coming up, like nitrogen vacancy based centers qubit and so on. They are coming up, so people would obviously go for it. And the other than the transmons, the one which is catching up is this one, photonic based qubits, photonic chips. Okay, so as of now, more more explored qubits are transmon qubits and photonic qubits. Okay, so it's 4:20 right now. 21. We will just meet after the 5 minutes. So we'll quickly take 5 minutes break, and then we'll get back and we'll see what is actual electromagnetic theory in the next half. Okay, right? We'll just take a break now. Hello everyone, welcome back. Okay, so let me start a new drawn news worksheet so that it's better. Okay, right. So I'll start with the very simple basics of electromagnetic theory, and we'll go slightly to some extent an advanced level. So that is enough for our quantum computing. So as per the schedule of this QT-03 and 4 schedule, if you notice, what is required to be discussed is electrostatic charge distributions and magnetostatic current distributions I have to discuss. Okay, and these things anyway lead you to understand the applications of electromagnetic theory. You see, the current distribution or the charges moving, giving you a current distribution is going to create a magnetic moment. That is what we saw in the case of spin magnets, electromagnets or nuclear magnets. Okay, right? So to how did we go on to that level, the understanding wise, we will see today, just now. Okay, fine. So let me start with, okay, electrostatics. Very briefly, I'll go. I'll not get into the details, and it is enough for us. So I'll start with electrostatics. Okay, by name itself, if you see, there is electrons or charges which are stationary, the static. So you can give a name, a description as a charges in static mode. Okay, that is electrostatic for you. Let's say I have some charge Q. I have some very tiny small charge, test charge capital Q. Okay, right? Now, as per Coulombic force of attraction or repulsion, there exists a force between these two charges. Okay, for the simplicity, what I will choose, both are positive. Means there is a repulsion between small q to large q. Okay, so what is that? The Coulombic force. Coulombic force we can use to calculate what is the repulsion force. Okay, wait a minute. Let me write down correctly. So Coulombic force, Coulomb force or Coulombic force of repulsion is F is equal to, it is directly proportional to the charges and it is inversely proportional to the distance between the charges. It acts in the direction of distance, the vector which is connecting them are, let's say, this charge is, the source charge is located at, let's say, R Q, and test charge is located at R capital Q. Now, what would be the R vector? So the R vector here is, you can just do RQ minus R small q. Okay, and R cap is along in that direction. Okay, so this is a force for you, and it's a proportionality is there. I have to use some proportional constant, which is 1 by 4 pi epsilon naught, where epsilon naught is a permittivity of free space. So I am taking the two charges in a free space. If I am considering in some kind of a material, like a some medium is there, I have to use the permittivity of the medium. So instead of having a free space permittivity, I should use the permittivity of that medium, or permittivity, or you can even say dielectric constant. Okay, right? So now this is a force of Coulombic force of repulsion, but we are not only confining to a single source charge, right? Let's say there are multiple source charges around. Let's say there is a Q1, Q2, Q3, but I have only one test charge. Okay, and beauty of this electrostatics is, right? The beauty of electrostatics is it doesn't matter how many charges are there. The force experienced by the test charge from all the source charges is a simple combination or just a superposition of all the charges. Okay, so the electric or coulombic force experienced by this test charge is a simple superposition of all the forces. Doesn't matter how many forces are there. Okay, so I simply write down overall total force on test charge Q is what is the force due to one first charge, what is the force due to second charge, and so on up to, let's say, n charges. Okay, and similarly you can write down overall expression is 1 by 4 pi epsilon naught. So Q is capital Q is common. Inside the bracket, you are going to put Q1 R1 cap R1 square, absolute square. I'm sorry, absolute square plus Q2 R2 divided by R2 absolute square means magnitude square. So this will go on up to here. Okay, so the overall force is like this. Now, whatever is there inside this bracket, this is the overall effect due to all the charges, right? Overall electric field due to all the charges. What you can simply do is put all these things, entire thing inside one element. It's called electric field due to all the charges. Okay, and send even the constant inside, and you are just going to say overall force is equal to the test charge magnitude multiplied by total electric field due to all the charges. Okay, so the electric field here is 1 by 4 pi epsilon naught. Okay, charge due to first one divided by its distance from the test charge, and Q2 divided by R square and so on, Qn Rn Rn square. Okay, so this is how we are going to write down the overall electric field due to all the charges. Okay, fine. So let's go for that. Fine. Okay, so let's go for that. Now I have counted the charges as individual elements, right? So they are discrete in nature. Let's say the charges are continuous in nature, means there is a wire which consisting of all the charges. In that case, how should I write down the electric field? That's a question. So continuous charge distribution, continuous charge distribution. We just saw discrete charge distribution, means I can count individually all the charges. In the case of continuous charge distribution, okay, first thing, let me take a wire. Okay, so in the wire, let's say charge is distributed equally, uniformly with some linear charge distribution lambda, means for every small length there is a some charge. Okay, so lambda distribution, lambda. So small element will take length element dl prime, or like from now on we will associate prime for source and no prime for test charge. Okay, and let's say there is a point Q is located at some point. So its a distance is, let's say, how much distance? R. Right? Now, so how much charge will be there in this small element dl, which is simply lambda multiplied by dl prime. Okay. Now, if you go back and see in the electric field equation, there is no description of test charge. Only the description of source charge is there. That is enough for us. So I don't care how much test charge, where it is located. Okay, location probably yes, but how much is, we don't care. So we simply write down what is the electric field due to this small test charge, which is simply equal to 1 by 4 pi epsilon naught. How much? Lambda dl prime divided by how much distance? R square. Okay, right? And probably it is along the connection between the source charge and the test charge. Now this is there. Remember, you need to put a prime wherever is source I am talking about. Now, let's say I want to know about the entire length of the wire. What is its electric field at that point, charge point Q? So what I'll do? I integrate the entire thing throughout that length. So I would be getting the entire electric field total. Okay. So remember, this is just a linear integration, single integration. Now, let's say I have a surface, a plate is there, some kind of a plate is there, okay, thin plate, a metallic plate, and on entire plate there is a charge distribution. In that case, how should I calculate the electric field due to this charge distribution? Okay, we just saw line integration, and similarly we can do surface integration. First of all, let's say this entire plate is consisting of charge uniformly distributed with some areal distribution like a sigma. Okay, so which means if we just take a small surface element of area dA, okay, and how much charge will be located in that? dq, which is equal to sigma into dA prime. Okay, the moment you know this, is finding electric field is very easy. So small electric field due to this small element is equal to 1 by 4 pi epsilon naught integration over the entire surface. Sorry, not integration, not right now. We will still write for the individual case. Okay, right? Individual case, small element. Wait a minute. So small element is dq r cap by r square, which is equal to 1 by 4 pi epsilon naught sigma at position r prime multiplied by dA, okay, multiplied by the radial vector connecting the source and test divided by r square. Now if I want to know the entire electric field due to the entire surface, what I'll do? I integrate along the x-axis, integrate along the y-axis, and I'll have overall electric field, which is E is equal to 1 by 4 pi epsilon naught integration over two dimensions. So sigma r prime, okay, okay, dA prime r cap divided by r square. Okay, dA prime probably equal to dx prime and dy prime. Okay, so in this way I'll find the entire electric field due to the entire surface. Now you can extend this to some kind of a volumetric charge distribution. Let's say some clump of some metal is there, the entire thing is having some charge, okay, which is distributed with some rho uniform distribution. Now you take a small volume element on that, okay, small volume element. So which is, let's say the volume element area is some d tau, What is that? D tau prime is equal to dA prime, dy prime, dz prime. Okay. So this is a volume element. Now I want to write down what is the electric field due to this small volume element. Simple. 1 by 4 pi epsilon naught. Okay. D tau prime multiplied by rho. This is a charge due to that. Okay. Divided by r square. If I need to know the entire thing, entire electric field due to the entire clump of charge, you simply integrate over x, y, and z. Okay, rho at r prime d tau d r prime wholes divided by r square. So we just saw how to find electric field due to linear charge distribution. Okay, linear charge distribution. Just a minute. This is linear charge distribution and surface charge distribution and volume charge distribution. Okay, right? Now, there is one important thing we should notice here. Okay, right? If there is a single charge, if it is a positive charge, if you notice, the electric field lines are actually diverging. You see, electric field lines are diverging, going away, and the length of this electric field lines are large at very close to the center of the charge. As you go further away, the length may go smaller and smaller. What it represents? It represents the strength of electric field reducing, going away from the source charge, because the distance dependence on the electric field is inversely proportional. Due to that, as you go further and further, the intensity of electric field would reduce. Okay, right? And one more way also you can determine the strength of the electric field is, if you notice around the charge, if you notice around the net, see, there are more field lines. If you go away, let's say I want to find the electric field line, electric field strength here, away from the source, there is only few field lines. So the strength is obviously low there. Strength is very large at the center or the near the source. Okay, and so remember, electric field lines are always diverging, spreading around. Okay, they're always spreading around. And when I have, let's say there is a positive charge, there is a negative charge. What happens in this case? From positive to negative, there is a field line. You see, right? So from positive to negative, there is a field line. And out of positive charge, field lines are coming out. Negative charge, field lines are coming in. Okay. So basically, these field lines go and connect. Okay. Something like that. Fine. So basically, it is just like a small magnetic dipole, but here I have a electric dipole. Okay. So only difference in electromagnetic to magnetostatics is, so electrostatics to magnetostatics is, there is a single pole, monopole can exist in electrostatics, and there is no chance of having a monopole in the case of magnetostatics. We'll come to that soon. Okay. Now, we just saw how electric field could be written in terms of, okay, the charge distributions. Okay, just now I was telling you about electric field. Actually, electric field lines are actually diverging. Okay, since we are talking about something called diverging, let's introduce some mathematics of requirement for our discussion for today and tomorrow. There is something called a gradient operator or del operator people call. So the del operator means the derivation of some entity along the x plus along the y plus along the z. This is called del operator or a gradient operator. Okay. So if there is a scalar field, okay, how it is varying along in all this direction, you will find it as gradient of that field. Okay. So this is called a gradient. If some field actually varies with respect to x direction and y direction and z direction is a scalar, it is going to have gradient. Okay, right? And the same del operator can also acted on some vectorial potential, some vector. Okay, some vector means the gradient, sorry, del operator is a vector. You can have a cross product or a dot product, dot product between some vectorial potential. This is called divergence. Okay. So it is also a dot product between the del operator and the field operator, vector field operator. Okay. So this is a gradient, how the vector potential varies along the x, y, and z. Let's say if I want to climb a hill, I'll choose the less steep version. So basically what I'm doing, I'm finding the gradient in particular location or various locations. I'll choose the less gradient version. Okay, right? So the next, this divergence means electric field lines are diverging. Okay, so the electric field lines are diverging. Okay, there is a very good gradients there. Means divergence of electric field is more than zero. It is not zero. When can I have zero divergence? Let's say the field lines are going straight. Straight. They are not even curving around. So they are going straight, so the divergence is not there. So this, let's say there is a field whose divergence is zero. It is like this. Let's say the water flowing along a river, its divergence is zero. But I can have non-zero divergence even in the case of straight following. What is that is, there is the field lines are initially very small, later on they pick up, later on they pick up, okay, speed or less strength. Let's say there is a flat region, later on it becomes a slant, a very slant. It's like somebody like a slippery slide they do in the park, right? So initially they come very slow and later on it picks up. And so there is a positive divergence in this case. So this is the divergence. 1 minute. Let's divergence of field is non-zero even in this case. Okay. Right. So if you notice, electric field is the best example for diverging field. So the mathematics help me to understand the electric field lines. Okay. Now, since I'm talking about a del operator which is vector, I can have some vectorial potential, the vectorial field whose, okay, let me take some other notation. Okay, and let us say okay, 1 minute. Okay, so some other potential representation I'll take, let's say A. I have potential where gradient, sorry, del, a cross product with that is non-zero. Okay, so this is vector, this is called a curl of A. So this is possible only when the vectorial field is curling around. What I mean is, let's say if you see tornadoes create, okay, so the field lines are the something which is rotating around, okay, right? Something is rotating. Now looking at this figure, you can easily recognize if I have a current carrying wire through the center from into the paper or something, so current carrying wire develops a magnetic field around. Okay, So that magnetic field lines are going to be a circular. They're going to be around. Okay. So this current carrying wire is going to create a magnetic field. So you see the curling of that field is non-zero. Curling of that field is non-zero. Fine. Okay, let me reload. Mhm. Yeah. Right. Okay, so there are some questions were asked. Interesting. We'll come to that. Okay. So the curl of A is non-zero, which means the fields are rotating. The field lines are rotating. When the curl is going to be zero, let's say the take situation where field lines are going straight. Okay, going straight, right? So in this case, curl of, let's say this field is B. Okay, I should not use B because B is reserved for some magnetic field. So some curl of some okay, M. No, M is also used. Some N is zero in this case. Okay. Let's say I have a field lines like this. Very interesting. So there is a field lines of equal strength at the top, and there is a very small at the bottom. Okay, in the bottom there is a small and there is a large. So this is a non-zero curl. You see, even though they're straight line, so the curl of this kind of a field is non-zero. You know why? If you place some kind of a stick here, some stick, it is going to rotate, right? So that is what whirlpool is created in a flowing water sometime. In a river, there is a hole, the river water is flowing smoothly. Wherever there is a hole at the bottom, you see something is rotating. Okay, so this is a mathematical del operator is going to help us in describing electric field and the magnetic field. So there is no harming knowing the 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 implications of this del operator and use that to understand how electromagnetic fields are going to be described. Okay, right? So now, there is a couple of questions here, and we'll just take those questions and then we'll wind up for today and we'll discuss a little more tomorrow. And we'll talk about the current distributions tomorrow and the next session, whatever is supposed to be required. Okay, there's a question here uh, by Vinod G. If negative divergence, then what it means? Very good question. Okay, so come back, right? Where is that? Where did we discuss the positive divergence? See, something is spreading around is a diverging, something exploding, something which is unexploding, which is getting compressed just in opposite direction. Okay, right? That is something called imploding, not exploding. So means something getting in, something is getting in like that. Okay, so that is a divergence of E is negative here. For which situation? For a situation of negative charge. So negative charge, the field lines are going into the charge. So that is a negative divergence. So another example in real world, if you notice some time back it happened, somebody went into the sea at a very, very low and there was an accident. Some billionaire who is the owner of that company which makes that vessel, and there as they went into very, very low, there's a pressure is so much from all the direction and the entire vessel got just crushed into a very small size and it stopped exploding, it just imploded. So the field, the force on that vessel is acting from all the directions. That is what we see. Okay, in the case of imploding, there the divergence is negative. Okay, right? And you are talking about, okay, so the curl. Okay, so that's a question from Vinod J. And next there is a question by Keshav Rao Ji is asking, curl is non-zero how? Okay, and we will see, right? So how curl is non-zero? Here I have only giving a simple example, okay, where if the field is rotating, corresponding to that field, the curl is non-zero. What is the curl mathematically? Curl of A, let's say A is a vectorial field having AXI plus AYJ plus AZK. All right. And what will be the curl of A? Curl of A is I cap, J cap, and K cap. Okay. Dou by dou X, dou by dou Y, dou by dou Z, AX, AY, and AZ. So you have to find the kind of a determinant of this matrix, and you would get what is the curl of J. So for this particular field, the example which I have given, this determinant is going to be non-zero. Okay. So in which case, in real world scenario, in which case, if you notice a current carrying wire, if you notice, it is going to create a magnetic field lines around. Okay, wait a minute. A current carrying wire creates a magnetic field lines around which are curling around. So there is a magnetic field. Okay. In fact, this magnetic field is equal to the curl of some A. So the magnetic field having non-zero means the curl of some magnetic potential is non-zero. So A is a non-zero curl potential. Okay. Or a vector potential having non-zero curl. Fine. So we'll see this tomorrow. Don't worry. And the explanation would be in terms of mathematics, not a very basic, simple description. Okay. Right. So, yeah. And if what I will be doing, okay. So I quickly add some notes for tomorrow, and if somebody is really interested can quickly go through it, and I'll be touching few points here and there in the notes so that you would really appreciate what I'm discussing for the today's session and tomorrow's session. Okay, so it's exactly 5 now. Okay, so I'll stop at this point. I'll hand it over to the academic. Thank you all. I'm just going to upload the notes. And the PPT also I'll upload.
Thank you very much, Ashwath sir.
Thank you, sir.
Yeah, all questions have been answered, and tomorrow we will meet for another 2-hour lecture on same topic, electromagnetic theory applications. So we'll understand how to go about. So these were part of QT-04 series, but we are covering a combined course, hence may not be more programming but theoretical. So we will meet tomorrow at 3 o'clock. Till then, we will take a break. Please remember, today is the last date for QT-04. Quiz 3 of QT-03 and 04. Quiz 3 is last today. Today midnight, please complete all your attempts. Right? We will meet tomorrow. Right? Thank you.
Sir, can I get a QT-03 and 4 canvas? Let me see.
We'll send the access. Yes, sir.